Okay, right, we're going to move on to our next speaker. And our next speaker name is Professor Justice Aheto. Now, Justice is a professor for biostatistics from the University of Ghana. Now, in 2021, he was actually recognized as a Black hero of the operational research, Black hero of operational research by the Operation Research Society. Well done, you. Now, actually today, he's actually given a talk at a conference in Seattle, also in America, at the Institute of Disease Modeling. So we're actually following a bit of a statistical theme. So shall we hand it over to Justice? Away we go.
He just needs to share his screen.
Okay, Justice, it's over to you. Share your screen. Very good to see you again, my friend. Right.
Yeah, very good. Very nice to see you too. I mean, it's been a pleasure to always be with the bright heroes of mathematics, where my inspiration started from, far back in the UK. So it's always good to come back to my home. Please, I mean, they have to allow me to share my slide. It's currently not been allowed. Yeah. The host, you allow me to share my slide. Yeah.
I'll make you co-host. Oh, sorry.
So what time is it over there in Seattle right now?
Yeah, at the moment it's 6:04 a.m.
Oh, okay.
6:04 a.m.
Well,
Yeah.
thank you for that commitment. I hope we haven't got you up in the morning.
No.
Too early.
No, I'm actually used to this time, so I'm good to go.
Good to go.
Yeah.
Okay, we're just playing you co-host. It's very good to see you again, my friend.
Yes, it's always a pleasure seeing you, Nira.
All right, and you're good to go.
Yes, so I'm just putting the PowerPoint mode now. If you can confirm, you can see my screen.
Yep, we can see your screen and it looks brilliant and you're ready to go. So the floor is yours.
Thank you very much for once again the opportunity. And today I will simply be delivering on spatiotemporal modeling and interactive web-based spatial mapping of malaria risk under the Integrated Nested Laplace Approximation, which is aimed at supporting and preventing control efforts in Ghana. So this is simply my outline for the presentation. As we all know, malaria is a deadly infectious disease and also considered as a severe global public health problem. In 2022, about 249 million malaria cases were recorded globally, out of which 608,000 deaths occurred. This is against the 241 million cases recorded in 2020, associated with 627,000 malaria deaths. Now, those who had the hardest hit are those located within Sub-Saharan Africa, where about 90% of all malaria deaths occur, with children under 5 accounting for almost about 78%. Ghana is of no exception. In fact, in the 2022 malaria cases data, Ghana happened to be among the top 11 global malaria burden countries, with 5,316,000 estimated number of cases in 2022, generally. And in Ghana specifically, malaria is responsible for about 20,000 deaths annually. And this contributes to about 25% of those aged under 5 years. Now, clearly, we can tell that this is a serious threat to achieving the Sustainable Development Goals, especially SDGs 3.2 and 3.3, where the 3.2 aimed at reducing neonatal mortality to at least 12 per 1,000 live births, and under 5 mortality to at least as low as possible, 25 per 1,000 live births, where the SDG 3.3 aimed at ending the epidemics of AIDS, tuberculosis, malaria, which I'm focusing on now, and neglected tropical diseases, and to combat hepatitis, waterborne diseases, and other communicable diseases by 2030. So given the successes that I've provided earlier, clearly we are actually not at a rate where we can achieve these SDGs 3.2 and 3.3. And given the limited public health resources in Sub-Saharan Africa countries like Ghana, it is very difficult and practically impossible to roll out universal interventions. Because for you to be able to do a universal intervention, you need to have sufficient public health resources and even the manpower to be able to do that. But having a limited public health resource, like in Ghana and other Sub-Saharan Africa countries, we need to target those who actually needed the intervention most compared to the general population. That said, it means that we can deploy tools like geospatial modeling, supported with some kind of interactive web-based spatial mapping tools, to characterize more localized geographical and time differences in malaria risk. This will provide the basis for identification of high-burden communities that might require urgent attention. As a result, what I'm going to present to you now is going to involve predicting and mapping more localized district level under 5 malaria risk from 2016 to 2021 in Ghana. And the goal is to support policymakers to make informed decisions for targeted interventions. The methods. The data used in this study is coming from District Health Information Management System 2 in Ghana over the period from 2016 to 2021. And let me indicate that this is actually a monthly collected data that is reported based on routine surveillance data across the whole of Ghana and for all the 260 districts. This is actually one of the respected national representative electronic medical record system implemented by the Ghana Health Service to collect and collate routine health service data in Ghana. I know there are several other countries that utilize the same DIMS2 process to collect electronic medical record system data. And DIMS2 data are actually aggregated at the district level, regional, and then national levels. And they include both in and outpatient records of suspected and confirmed malaria cases, which I'm using in this presentation. I have extracted data on uncomplicated confirmed malaria cases for the 260 districts in Ghana over the period 2016 to 2021 for the study. Here, the approach is to demonstrate how temporal modeling supported with actual-based mapping can be used to support policy decisions regarding effort to prevent and to control malaria. It can be applied to other settings as well. So in this study, my focus in terms of the outcome of interest is on number of malaria positive individuals per district, where the individuals here means number of children under 5 years. I try to incorporate or to demonstrate how explanatory variables or covariates can be included in the model so that they can help to explain some of the variabilities we might experience over the 260 districts and over time. What it means is that this is just to demonstrate the capability of the model to accommodate variables that can help us to mediate or understand how distribution of malaria cases can be considered across the district. Of course, in this study, I'm considering only 2, which is the number of children under 5 years per district and the number of male population per district. With resources, one can also include other factors at the spatial level, which we call the spatial covariate, like distance to the nearest facility. You can think about distance to the nearest water body. You can think about maybe proportion of mothers or maybe the population that has secondary education or special education. You can consider things like aridity, vegetation index, altitude, and all that at the geospatial level. But because this is a demonstration of how you can incorporate such covariate into the model, I played with these 2 variables. And also obtaining those geospatial covariate is very expensive because what it means is that you have to take the polygons of each of the districts and then try to gather the surfaces of those geospatial covariate, like the vegetation and stuff, and then create a buffer and then extract the mean values of those covariates. And this is very expensive. So at the moment, I'm just trying to demonstrate how you can incorporate all those into the model. And for future studies, definitely, with funding available, we'll move into that dimension. So here I try to provide the model behind the result that I'll be showing you in some few minutes. So here we identify the number of malaria cases recorded in each region, in this case, in each district as YIT at time period T. And then we denote the UIT to be the expected number of malaria cases recorded in each district in time t. And then we provide the NIT, which represents the number of persons at risk at district I in year t. Now, based on these three elements, that's the number of malaria cases recorded per district and the expected number of cases recorded per district, together with the number of persons at risk at district I in time period t, we can estimate the expected number of malaria cases recorded in district I at time t as EIT equal the NIT, which is a number of expected persons at risk at district I in time t. Then the summation of all those, those number of malaria cases recorded in each district. So if you have 260 districts, as it is in the case of Ghana, we are going to add all of them up over all the time period here. So we are summing over all the districts and all the time period for each of the respective districts and time to get a total number of cases, that's number of malaria cases recorded. And then when we sum up the UIT, what it means is that this is giving us the total number of persons at risk across all the 260 districts at that period t. That's what we are doing at the down here. So this quantity here, the summation of IT, YIT divided by summation of IT, NIT, is simply giving you some kind of probability or prevalence or incidence rate. Okay, that's what this one is doing. So given that, we can multiply that prevalence or probability by the NIT, which will give us the expected number of people who were diagnosed as being positive to malaria cases in each of the districts over each of the time period that we're interested in, which is from 2016 to 2021. So that's basically generating the expected number of persons at risk at district I in year t. The formulation for estimating standard incidence ratio can follow easily, or what you call the relative risk can be done without any struggle. Because once we know the total number of malaria cases recorded in district I over time period t, and we also know the expected number of persons at risk in each region, in each district I at time period t, we can easily calculate the standardized incidence ratio, which we will call the relative risk, simply by dividing the number of malaria cases recorded in district I over time period t by the expected number of malaria cases recorded in district I over time period t. So this is how we generate the relative risk. We can simply take the log relative risk as the log of the function we have here, which will represent by this function. So this is going to be on an increasing scale. And when it comes to modeling this relative risk, the easy way out, which is a very standard approach, is to deploy some kind of Poisson model, because this account, once this account, you can easily deploy a Poisson model in a special framework. So under this very study, we implemented a Bayesian numerical spatiotemporal specification for the Poisson model, where we take into account the number of malaria cases YIT observed in district I at time period t. So basically, you have the YIT conditional on the expected values or expected numbers, where we have the relative risk to be approximately, or to follow the Poisson distribution with parameters, the expected number of malaria cases in district I at time period t against the relative risk itself. So the relative risk here is the one that we're actually interested in, but because we need to take care of some offset, we add on the expected count that we have produced from the previous session. So like I said, we can take the log of the theta IT, which is a relative risk, to have it as a continuous function. And then we have the intercept here. We have some set of covariates with their for a vector of a regression coefficient for each of those covariates. Then we have a random effect here that is taking into account the structured spatial effects across the district. So this is talking about district I and all that. And we also have another component indexing the district, which is non-structured spatial effects at the district level. So what it means is that at the district level, we are going to estimate two quantities which are random effects, where we talk about the structured spatial effects and then the unstructured spatial effects. And because we are dealing with time also, we are going to account for the temporal effect using this quantity here. And this is something purely due to temporal effect, and something related to temporal, but not pure temporal effect, more like the residual at the time level. So this is what we are expecting to estimate. These are the parameters that we need to estimate. And we need to assume some distributions for these parameters. For instance, the precision for the tau here, we assume the normal distribution for the intercept, something that did not depend on anything, which will give us the overall average or mean. Then when it comes to the residual for the space, that is a district level residual that is not spatially structured, we also assume the normal distribution for that. Then we also have another distribution for the structured spatial effect, which is also normal, given these parameters. And then we also provided distribution for the temporal effect, which is the gamma t, which is also given the normal. And then finally, the time, the random effect with temporal, which is not purely temporal effect. That one too, we assume the normal distribution for that. Definitely, because this is implemented under the Bayesian framework or understanding, we need to specify the priors for all our parameters in the model. So here, when it comes to this quantity, we provided a gamma prior of 1 and 0.00 that, and all of other ones we provide the same prior, except for the ty, and then I think that's the only one that we provided a much smaller. So for all these, 1, 2, 3, these are all considered as an informative prior. The reason being that from the literature, we have not been able to identify existing priors for this kind of problem. So our best bet is to use what we call uninformative prior, where we are speaking less into the data, meaning that we are allowing the available data to speak for itself more than we speaking into it. So our priors are all uninformative. So what it means is that we don't expect this result to be too different from those who might be using the classical or the frequentist approach, because our priors are uninformative. Here I try to provide detailed, though I've explained this already, but I try to provide detailed parameter description for each of the parameters we have in there that I've just shown to you, so that those who might be interested in replicating this study can easily move along. But these are the things I've earlier on discussed. So I said the beta naught is overall mean or the average risk for all districts. Then the X transpose IT is simply a matrix of covariate, and the beta actually represent unknown corresponding parameters of or the vector of coefficient for risk factors considered. And the UI, like I said, denote the structured spatial random effect, or you can also call it the correlated heterogeneity effects. And then the VI also denotes unstructured singular spatial component that models heterogeneity or the uncorrelated heterogeneity effect among the locations at time t. So these locations are simply talking about across the district or among the district that we are taking into account over the time period. Then we also have the correlated heterogeneity effect, UI, and uncorrelated heterogeneity effect, VIT. These are what we are calling as a spatial random effect that can vary with time. The delta I actually represent a neighborhood of the IF area, in our case of the IF district, where the N delta I is simply the number of regions or districts in the IF neighborhood. You can also take the mu bar di to mean the mean of the neighboring UI, where we already know that the UI is simply the structured random effect on district I. Now, gamma t is simply one of the quantities where we actually provide the autoregressive Proud distribution, which we allow to follow a random walk in time of first order. And this will definitely allow us for a non-parametric temporal effect estimation. What about the faulty is simply representing the unstructured temporal effect that is independently and then identically distributed. Like I said earlier, because we don't have any reliable Prouds for our parameters, we assume or we assigned non-informative Proud distribution. And we approximated their posterior distributions by using the integrated nested Laplace approximation approach. How do we actually implement the model that I've just discussed with you? There's this package called the R-in-lab package, a very powerful package, of course, that is doing a lot of work around the Bayesian framework. And it's very fast and produces reliable estimates. So we actually implemented our model under the in-lab approach. It is very powerful estimation procedure. We all know that this actually is one of those packages that combines analytical approximation and the numerical integration to obtain the approximated posterior distribution of parameters. And it's been widely used in spatial models, including other areas as well. As one of the key interests in this modeling is to be able to develop an interactive web-based spatial tools that can support better visualization of our estimates. As a result, we utilize leaflet package and others in R to achieve the development of the interactive web-based mapping tool for this study. So let's look at the results. So I'm going to demonstrate the results first, then we can look at the spatial variations that were estimated across all the 260 districts in Ghana, and how I've been able to develop the interactive web-based mapping tool to improve visualization for targeted interventions for malaria. So these are the posterior distributions and the associated the Bayesian credible intervals of the relative risk that we want to estimate. And remember that this is actually a spatiotemporal model covering a period from 2016 to 2021. So here, the first model, which we call model 1, is simply an empty model. This is a model that we did not take into account any covariate, just to, estimate the relative risk across the district, the 260 district in Ghana, without taking into account any explanatory variable. And then we also take into account some of the model evaluation metrics just to see how the two models will compare. That is taking into account any covariate and then without covariate. That's what we are trying to do here. So the parameters you can see, I'm just demonstrating how you can incorporate maybe explanatory variables or covariate into your model while taking into account spatial and temporal effects under the district level kind of estimation. So in model 2, the same quantities that we have produced. So the difference between model 1 and model 2 is that in model 2, we incorporate what we call covariate or explanatory variables, while in model 1, it's purely a null or an empty model. Now, if you look at the model metrics, it's telling that clearly model 2, which is a more complex model, is not doing too much better than model 1, even though the DIC and the WIC, which is the difference formative criteria, and the Watanabe-Akaken formative criteria, which we normally use in the Bayesian framework to measure model metrics, is indicating that there's not much improvement in moving from empty model to incorporating some kind of covariate into the model. That is based on this data set. Because if you look at the DIC, this is 2112.0.75, this is 2112.0.45, very small reduction in the deviance. And if you look at the Watanabe formation criteria also, this is 2065.0.21, and this is 20,649.65. The reduction is very minimal. Okay, so clearly any of these model could do. But because the interest is to demonstrate how you can also incorporate covariate, we prefer model 2. In any way, model 2 is doing relatively better based on the DIC and stuff, but it's not doing too better. But for you to move from a simpler model to a complex model, you need to look out for the gains that's been made. You move from the simpler to the complex before you can consider that. So here, we are simply using model 2 for all our further analysis and then spatial mapping and stuff. Okay, so here we are now going to look at the spatial and the temporal variations in malaria risk supported with the interactive web-based mapping tool as discussed earlier. The first is about the spatial variation in the relative risk of malaria across all the 260 districts in Ghana from 2016 to 2021. So these are the relative risk. Looking at it from 2016 all the way to 2021, clearly one can tell that the risk of malaria across the 260 districts in Ghana is not constant across time. For instance, if you look at some of the rates in the 2016, and you come to look at that of 2017, there's a lot of variability. But sometimes looking at it with your eye like this, physically like this, sometimes it's problematic. You can tell that yes, there's a change, but as to the law of change from one period to another across the same district, we want to see what is happening. So if we want, we can take this one. If you look at 2016, where my cursor is here at the topmost part, where my cursor is. If you look at this in 2016, you can fix yourself on the same district in 2016 and then look at the same district in 2017. So here, to allow for comparison, I have fixed the scale. As you can see, I fixed the scale across all the study years. I've fixed the scale so that we can easily compare across all the study years from 2016 to 2021. So I'm able to compare the risk across all the 6-year time period that we are looking at and across all the districts that we are considering. So if I fix myself here at the top here, I see this is around 1.1 to 3.0 risk. And then I move to the same district here in 2017, and you can see that this one is showing something that ranges from 0.99 to 1.10. Okay, so at least there's some kind of a difference in that. Actually, it's a reduction. So meaning that in that district, there was a reduction in relative risk from 1.10 to 3.11 to 0.99 to 1.10 in 2017. So those are the things we're interested in. We're interested in either the risk of malaria cases is constant across districts over time or is changing. So that is it. But for policymakers, this might not be too useful to them because for each of these districts, even me who is a Ghanaian, I can't tell the name of all the districts in Ghana. So if you're using this to support a policy making decision, it means that you need to develop a tool that can easily help policymakers identify this district easily and also to know the exact risk at those locations. If you look at the scale that are provided from 0 to 0.99, 0.99 to 1, you could see that some districts might even have 0, but they belong to the first scale. Some might even have 0.05, but they belong to the same scale. Some might have 0.2 or 0.5, they belong to the same scale. But as I said earlier, optimizing public health resources simply means that you need to know exactly what's happening at a particular place. And so you can plan appropriately the little resource that you have to target them. And that actually led me to develop the interactive web-based mapping tool, which I put here. It's a standalone application. So you don't need to host this on any website where you have to pay some money to be able to host it. No. I can send this to you directly to your email, and you can always play with it, and you can see visually what is happening interactively. So to demonstrate that, I need to skip from the presentation mode to the normal PowerPoint like this. I want to know if I'm sharing the entire screen or something. So let me do this first. And if in case I'm not sharing the entire screen, please kindly draw my attention because as soon as I click on this, it's supposed to open. So I'm going to demonstrate the utility of the web-based tool that I've developed to improve visualization and to support policymakers make a better decision with the little result that they will have. So I'm starting with 2016 just to demonstrate that one, and also demonstrate 2021 because it's similar. So what I need to do is to open this guy, double click this guy, and to be asking me permission if I want to open this. Please, can you confirm if you are seeing the dialog box that just opened? Can you confirm?
Yeah, we've seen a icon.
Okay.
Yeah.
Okay, that's cool. So all I need to do now is to click on open icon here. So open. Can you confirm you are seeing my current screen?
No, I don't think so.
What can you see? Can you see something like a web-based something?
No, what we're seeing is your PowerPoint slide.
Okay, then maybe I need to share the entire screen.
Yep.
So I'm going to go up the sharing and share again, where I will share my entire screen.
Right.
So share screen, share. Okay, so I'm going back to start the process again.
Yeah, excellent. Now we can see it. We can see your web-based solution, and it's looking fantastic.
Good, good. So let me go off and come back to the PowerPoint so that I can demonstrate that again. So what I did earlier is to double click this guy, and I go to open, and I click on that. And once you're connected to the internet, this opens up to you. So you can confirm that you are now seeing the web-based application, right?
We are now seeing the web-based application.
Excellent. So now the novelty in this process, apart from creating the static map, is to do this. So look at me. I'm going to put the cursor on the first one that I used to demonstrate on the static part. So let's put my cursor here. Can you tell me what you are seeing?
Okay, we are seeing observed district name, SIR, relative risk, standard error.
Excellent. Excellent. So if I give this map to a policymaker, which is a standalone application I developed also in R, all the policymaker needs to do is to put a cursor on a particular polygon, and it displays the relative risk highlighted for you, in this case 3.28. It gives you the observed number of malaria cases among the 5 children in that district for that year period. In this case, it's 12,923. And it also gives you the specific name of the district. It's telling you that in Ghana, the district that is recording this is Bongo district in Ghana. And the SIR for that district is 0.82, which we don't trust because this is just a crude rate. It is not coming from the model. It's a crude rate that we estimated from the data directly. Then instead of the relative risk for that district, which is Bongo, is 3.28, meaning that residing in Bongo is associated with an increased risk of testing positive for malaria because the relative risk is higher than 1, as you can see. So this is something that policymakers or those who will be the users of this app will not struggle to use or to understand. All you need to do is to put a cursor on a particular polygon, and it tells you all the statistics about that polygon, including the name of the district of that polygon. So I'm seeing another reddish area here, down here. All I need to do is put my cursor on that. And again, the same details are popping up for you. So this is a novelty about this very work that I want to demonstrate to you. So here it's telling me that this district is called BHoM Municipal. Okay, that's the district BHoM Municipal. And the relative risk over there is 4.22. And the total number of observed number of malaria cases among the 5 children for 2016 in that district is 17,409. And SI is 2.4, and the relative risk is 4.22. We financiated the standard error for the relative risk of 0.03. Okay, so here you don't need to be a sophisticated person in modeling, in spatial modeling, or understanding geography to be able to use this output for your work. Okay, so in case you want to target areas or districts where the relative risk is above, let's say 1, this is easy for you to identify. All you need to do is to put a cursor on the district polygon, and you know what's happening down there. For instance, let's come to this polygon here, this very one, where the cursor is. This is telling me that the relative risk in that district is 0.56, and the number of observed malaria cases in that district in 2017 is 8,833, and the name of the district is Northeast Gonja. The name of the district is Northeast Gonja. And when you come to SIR, it was 0.56, and also relative risk is the same, 0.56. The standard error for the relative risk is 0.01. Okay, so anywhere you move to, you get the same information. So wherever you go, you keep changing. If you change your polygons, you get what you want. So this is the beauty and the novelty about this application. The same way, as you can see, this is for the 2016. We can do the same for, let me pick the second one, let's say 2021, which is the most recent, and see what's happened over there as well. It's the same process. So I double click on the tool, I click on open, then it will start opening for me. Please remember that this is internet dependent. So you need internet to be able to display all this correctly. Very, very important. So when I come here, I can look at the Redis here. I have the relative risk of 3.09, observed number of cases 2473. And the district name here is Nanumba North. SI is 0.19, and then the relative risk is 3.09, as I said earlier. Actually, standard error here is 0.01. Okay, so as I move from one polygon to another, the same set of parameters are available for me, easily to see. So instead of struggling with the scales that are provided here to from 0.00 to 0.9, that's and so this app is able to give me the exact estimate at those district level with the district names and all other parameters of interest in the same thing. So, but still, there's a need. I'm moving back to my PowerPoint presentation now. Going back, there's a need to harmonize all these 6 years kind of estimate together. How do we put them together? I want to also develop another app that simultaneously can display all these 6 together for me just by putting a cursor. I want to have everything together. So that will take me to the next one. So I don't want to move from this slide now. So I'm going to the next one. Okay, it's the same set of prediction you have seen earlier and the same one. But this time around, instead of doing the interactive web base for each of them separately, I want to put all of them together and use a screenshotter to identify each of them at a particular time. So look at this again. I'm going to open this one where all of them, all the 6 maps are there together, and putting a cursor on one political area, it can show all other areas corresponding to that area for me for targeted intervention. So let's see. That will help me to determine either the prevalence is changing or the risk is changing from one location to another over time or not with a single click. So let's go. Okay, again, it's asking me to open. I say, okay, open up. Okay. So all the 6 maps that you have seen earlier, I have been able to put all of them together in a very interactive way, where if I put a cursor at a particular location right now, it will put a Redis icon across that same location across all the other 5. So I'm starting with this one, where we normally started from with this guy, which is a bongo that we saw earlier. So if you want to put a cursor on the bongo, you see that the red circles are all over showing the same bongo across all the districts. So if I want to see if the column seen at where I put the cursor is the same as where they put the red circles, it's easy for me. That is to determine if the colors are the same across all the 6 time period we are looking at. And if you look into the red icons, you could tell clearly that the colors are not the same. Some of them have very much reduced prevalence or risk, while others are very high risk. So for instance, if you look at this one, here is 3.28 relative risk. But if you bring the cursor to this one, it's actually giving you 2.01. And this one is actually going to give you different one, which is 0.85. And that's across all of them. But the good news is that once you put the cursor on any of them, the red circles will go around, identify the same location for you to see the colors to determine either the colors or the risk is the same across all the 6 time period or they are changing. And focusing on this district, which is the bongo district, you could tell clearly that the colors are changing, meaning that the risk is not the same across the Bongo district over the 6 time period that we are looking at. And that's the beauty of this one. I can move to another location with the cursor. Let's see if I put the cursor here. This is East Gonja Municipal. And you can see that the circle red will correspond to that location. And you can stay there and look at all the colors to see if the colors are the same or they are not the same. So this is the beauty of putting everything together rather than looking at them one by one. Okay. So this is another one, another way of demonstrating the novelty in this very way that I've done. Again, don't forget that we still maintain the scales. We fix the scales across all of the 6 time periods so that we can compare. And aside that, once you put the cursor, you get the specific value for that district rather than having an interval value for that district. Okay. Now, again, this I feel is not sufficient for me. So I decided to do some kind of graphic interchange format, also to display either the risk across all the study districts is changing over time or not. So here I use the graphic interchange format, also in R, to produce the same thing, where I will show you only single map, but that single map that I'll show you, you see it changing over time. So I think that one I don't need the interactive part. So let me just go to the PowerPoint mode. Okay, so there we go. So just look at the map and tell me what is happening.
Okay.
So assuming there's no variation in the risk of malaria across the 260 districts in Ghana, we don't expect any changes in the colors because we fix the interval. We fix the interval so we can compare. So assuming the relative risk across each of the districts over the 6 time period that we are looking at, then when you move from 2016 to 2017, we should not see any variation in the colors. But because there's a presence of variation from one district to another and over the 6 time period, if you look at the graphical interchange format that I've produced from R that you're seeing right now, you could tell that depending on the time you're looking at, the colors keep changing at certain locations. Well, some of them seems to remain constant, some of them keeps changing. Do you see what I'm talking about?
Yeah, we can see it, yeah.
Okay. So this is where, if you're interested in just producing a single map by showing the result over the time period in a temporal way, you can also produce the graphic interchange format in R to show you all this. So this is a confirmation that the relative risk across each of the districts across from 2016 to 2021 is not constant. It's actually changing. But you can see that some of them seems to be stable, but others are changing. Okay. So we go to the next one. So in our practice, it's always good to produce uncertainties associated with your estimate. It's always good to produce uncertainties associated with your estimate. So the relative risks that you have seen, what I'm showing you right now, these are the associated standard errors for those relative risks across the 260 districts from 2016 to the 2021. And generally, the relative risk across all the years ranges from 0 to 0.04. Generally, very, very small, meaning that the uncertainties around our estimates are not too much. They are very, very small, meaning we expect our estimate to be very much reliable for decision-making purposes. Okay. On that note, I have some key findings. So both the log number of children under 5 years and the log number of males were significantly associated with a number of malaria cases observed. And then we found that the Laura and the Nadam district in the Upper West region recorded a higher relative risk, except in the year 2020. The majority of the districts and municipalities in the Savannah, North, and Bono East regions recorded a high relative risk of malaria over the entire period. And we also noted that the uncertainties associated with the predicted relative risk are very low. The strength. The model approach that we have adopted actually allows us to borrow information from districts that might have smaller counts, from districts that might have a larger count of malaria cases to create predictions, and the supported interactive based special risk map for the whole of Ghana. There are some limitations. It is very important to also include some geographically indexed malaria data on policy intervention over time. Also, reporting car rate for each of the districts can be included. Distance to the nearest water bodies, type of housing, which influence malaria transmission a lot, including geospatial coverage, which might explain some of the geographical differences we observed across some of the districts. Inclusion of this can also help to improve our understanding about the transmission across children under 5 years, across all the 260 districts over the 6-year time period. Conclusion and policy implications for this study. The geographical and the temporal differences that we observed are clearly a serious threat to achieving the SDG 3.2 and that of 3.3. The findings from the present study provide a critical tool for malaria surveillance and elimination. It also helps us to assess the progress that we are making in the fight against malaria at the district level in Ghana. The findings can be used by local, national, and global decision makers who are responsible for the health and survival of children to 1, better understand more localized district level patterns of under 5 malaria risk, and also to design more precise, high impact policies and intervention strategies to reduce malaria burden and interstate mobility and mortality in the country. I have some further research that we can explore. For instance, would there be some other social norms, contextual and distinct levels of geographical variation that could possibly help us to explain the spatial and temporal variations that we observe in the study? If yes, it means there should be a further study to incorporate those kind of factors. I need to do some acknowledgement. Bill and Melinda Gates Foundation for funding some of the works that I do. Gavi, the Vaccine Alliance, also for funding some of the work that I do. The College of Public Health, University of South Florida in the US for some of the collaborations on some of my projects. The World Pop, University of Southampton in the UK, where I'm currently serving as a visiting research fellow for all the collaborators that we enjoyed so far. And all my other research collaborators, I acknowledge them. I must also strongly acknowledge the Black Heroes of Mathematics UK for always giving me the platform to showcase what I do and also to being there for me all the time. And Prof. Nira and other team members at K Aheto, and very thanks for all the continuous engagement. And also to the London Mathematical Society in the UK for having very influence on my modeling skills and always being there and trying to showcase the work I do publicly to the world. I appreciate all that. I have some references for those who have been interested in the work I do and generally the work of other people in this field of study. On that note, I have a chance to say a very big thank you for listening to me, and I'm happy if there are some questions to answer. Thank you.
Okay, thank you. Okay. Just this time is against us, so I only really can just say one comment, but what I'll do is that we will forward on to one question to, questions to you. But I will say this, is that very much so is that the measure of a mathematical model is to, 1 is to understand, 2 to predict, and 3 is, and more importantly, is to influence. A mathematical model that actually can influence policy and influence direction, that shows how quality and beautiful that model is. And in terms of what you've been doing in terms of malaria in Ghana, actually influencing the policymakers to come up with the necessary interventions to reduce malaria in Ghana, I have to say respect to you and respect to the models that you're doing, and thank you very much indeed. So I have to give you a round of applause. Yeah.
Thank you very much. I appreciate all that. Thank you very much. I'm grateful.
All right. Thank you very much indeed, my friend. Okay, so that's the first 2 sessions of the 2 talks at the Black Heroes of Mathematics Conference. Now we're going to have a short break. We will be back here for about 3 o'clock for our next talk. And yeah, have a nice break, and I'll see you back here for 3 o'clock. Well, again, thank you very much indeed, Justice. Thank you. Thank you.
Yeah, thank you. There was a question for me, but I'll answer in the chat. Yeah.
Yes.
Yeah. So
I think we're going for a break now.
Yeah, we're going for a break.
Let's have a private chat. If you can answer the question in the chat, and then I'll pass your answer on for you.
yeah. So basically, I mean, sex
Yeah,
actually, let me just finish it. Let me just finish it. Basically, sex is one of those that were identified to be predictors of malaria in certain groups. So what I try to do is to find the proportion of male, it can be proportion of the male or the proportion of females who actually is in the district. So I treat that as one of the covariates. Thank you.
No, what we need to do is just before, because
okay.
you're off to the end, aren't you? So you just log on as a panelist, I'll make you co-host and you just show your screen, so the same as the people online. Very good. Very good.
Oh, here we go. Hi, Justice, can you hear me?
Yes, I can hear you.
Oh, well, thank you very much indeed for that. That was, you know, I really, we gotta see that paper. We gotta see that paper. That was a real, you know, a really, you know, in terms of, let's say, modeling principles of, you know, of impact, yeah, impact and influence. That's a measurable model. But so thank you very much indeed, yes?
Thank you. Thank you. I'm grateful. Thank you.
So, sorry for speeding you along, but you know, we had the next speaker coming, you know, in the
Yeah. I
yeah.
understand. Yeah.
No problems, no problems. Yeah,
Yeah,
and as
okay.
for our next speaker.